So once again, hello future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like my videos, please don't forget to subscribe and share my videos to your friends so that you can also help them improve in their chosen course, especially civil engineering. And I uploaded materials so that I can help students in civil engineering, especially civil engineering, and also in other allied uh, engineering courses. So once again, to keep me energized and keep me going so that you can also inspire me and help my channel, please don't forget to share my videos. So once again, this is my favorite method aside from double integration and Castigliano's second theorem on energy method, the conjugate beam method. So for the beam loaded as shown by conjugate beam method, determine the deflection at B and at the center when the uniform load covers the entire span. At the center when the uniform load covers the entire span. So let's select A as our moment center in preparing the conjugate beam. The conjugate beam remains the same, pin at the left, then roller at the right, because the beam is end supported. So moment due to the loading, there's no need to compute for the reaction. 24 times 4, 48 times 2, so 96 over EI second degree. Oh, sorry, 24 times 4 is 96 times 2, so 192 over EI second degree. So the moment of the reaction at A about A is, moment of the reaction at C about A will also be 192 over EI, but it is triangular. So first, let's solve for uh, theta C in this case, so that when we consider BC later, it will be simpler. So call that theta A, then downward at C. That's the positive slope at C. At the left, just like Sines convention for shear, upward at the left section, then downward at the right section. Then that's the area equivalent to that force there. Moment arm from the left is 10 thirds. Then this is downward. Then the distance of the centroid of this area from the left is 4 over second degree plus 2. So 4 over 4, that's 1 meter. So moment about A equals 0, clockwise positive. So theta C times 10. Then plus, this area is 1/3 of 4 times 192 over EI times 1. 4 over 4 is 1. Then minus 1/2 or 0.5 of 10 times 192 times 10 thirds. The moment arm is 10 thirds. Solving for theta C is equal to 294.4 over EI. Then let's consider BC. So if we consider BC, B will be the left section. So the positive slope is upward. And the positive deflection is clockwise, as shown in the figure. So theta B upward, positive deflection is upward. So always assume positive so that if the result is positive, it's really positive. If the result is negative, then it's really negative. So to solve for theta B, we sum up forces vertical. This is the equivalent force upward. So theta B plus 0.5 of 6 times 115.2. By the way, 115.2 is by similar triangles. Ordinate here as to 6 equals 192 as to 10. So 6 over 10 is 0.6. So this is 0.6 of 192. So you just apply similar triangles. Then minus theta C, which is 294.4 over EI, then equals 0. So theta B equals negative 51.2, which is the same answer as in the other methods. Then for deflection at B, summation moment B equals 0 considering BC. So moment B equals 0 equals delta B, then mine plus delta B plus theta C, which is 294.4 over EI times 6, and minus 0.5 of 6 times 115.2 over EI, then this moment arm is 1/3 of 6, which is 2. So minus 0.5 of 6 times 115.2 over EI times 2. So we can now solve delta B. Delta B equals negative 1075.2 over EI, just like before. Then when the load is at the when the load covers the entire span, so this is now the situation, and we find the slope which is expected 0 at the center and maximum at the center. So 24 times 10 times 5 at, let's select C as our moment center this time, and this is second degree. So 5 meters, 5 meters. So 24 times 10 times 5 is equal to 1200 over EI. So the moment of the reaction here about C is also 1200 over EI, but triangular. Then at the center, the ordinate at the center would be half of 1200 because this is the center, so 600 over EI. So considering the entire system, let's put the slope, positive slope, and the equivalent area and locations, theta A and theta C. So moment about C equals 0, so theta A times 10, that's a positive direction of slope, or shear. Then plus 0.5 of 10 times 1200 times moment arm 10/3. Then minus this area, which is 1/3 times 10 times 1200. Moment arm is 10 over 4 or 2.5, 10 over 4, 10 over second degree plus 2, so 2.5. From here we can solve theta A. Theta A is negative 1000 over EI. Then let's remove this force. Let's consider A and the midspan only. And by the way, the value here at the midspan is 24 times 5 times 2.5. And that is 300 over EI. 300 over EI again is 24 times 5 times 2.5. Half of 5 is 2.5 at the midspan or center. So that's why you get 300 over EI, but this is still second degree. So let's now put the forces. This is 5/3 and downward for this loading here. Then let's put the positive theta M and delta M. So downward and counterclockwise for positive deflection. To solve for theta M, summation forces Y in this portion. So theta A, negative 1000 over EI, plus 0.5 of 5 times 600 over EI, then minus 1/3 of 5 times 300 over EI, then minus theta M equals 0. So expect theta M to be 0. So that's it. Then for delta M, summation moment about section M 0. So theta A, negative 1000 over EI times 5 plus 0.5 times 5 times 600 over EI times 5/3. So we just copy the area, then include the moment arm. Then minus, by the way, this distance is 5 over 4 or 1.25 moment arm of this force here. So minus 1/3 of 5 times 300 over EI times 5 over 4 or 1.25. Then minus delta M equals 0. Solving for delta M is equal to negative 3125 over EI, just like in the other methods. So that's it. So once again, don't forget to share my videos.